Hello again. I really don't want to make you sad here or anything, but this is the last of our chapters, our little chats here on the YouTube channel. So let's do chapter 12, fluid dynamics here. This is going to be short and sweet. And let's get started with a definition of fluid flow. When I have fluid that's moving in a pipe, I can talk about how much fluid is moving through. I could measure that in gallons per minute. I could measure it in cubic feet per second, or cubic meters per minute, or any kind of unit that I want. But that flow rate is going to be some kind of volume per time. All right. One way to calculate that would be, the easiest way actually, would be to take the velocity of the fluid times the cross-sectional area. And if you look at the units of that, velocity would be meters per second, area would be square meters, so that would be cubic meters per second, or volume per time, right? So that's a handy way to do that. When I have fluid flowing in a pipe, I can measure how fast it's moving through. But the trick here, and the thing that we want to put in on today's little discussion, is that if I have a certain amount of fluid passing through at this point, at some point here in the pipe, there's nowhere else for it to go, so I have to have that same fluid flowing at a different point. Even if the pipe chokes down, even if whatever. If I were to choke off this side completely, if I just close the spigot here, then this fluid is going to stop flowing, which means that there's no more room for this fluid to flow, so it all stops at the same time. And the water does not compress, it doesn't stretch out, it doesn't do anything. It's just, we say it's incompressible. That's almost true. But when I use that idea, then all I have to do here is say the flow rate at one point is equal to the flow rate of another point. If the flow rate is the velocity of the fluid at point 1 times the cross-sectional area of the pipe, A1, then V1A1's got to be equal to V2A2. It's a very simple formula, very simple idea. There's just, there's no secret room over here for the extra water to move into. So whatever you push into one side of a pipe, it's got to come out the other end. Now, what we've done here is we've drilled down into this A1. Typically, pipes are circular in cross-section. We're interested in the inside diameter, not the, we could measure from the outside of the pipe like that, but I don't have fluid flowing here and here, so it doesn't make any sense to do that. We're measuring from the inside of the pipe, that inner diameter. ID is an abbreviation that you'll see sometimes. A pipe might be 2 inches ID, or inner diameter, and that tells you where the fluid is, not the thickness of the wall of the pipe. Okay, so we're using that. Area is pi diameter squared divided by 4. I've done that on both sides. The pi's cancel, the 4's cancel. So this would be an alternative way to do it right here. Usually we have the diameters instead of the cross-sectional areas, so you can either put in the velocity in the area, or you could put in the velocity in the diameter, but you have to square the diameters, because remember, we're talking about square units. I need meters squared to make that work. Okay, let's try one of these. These are real easy. Let's say that I have a pipe that, we'll do this one in area, I guess. Area 1, I've got 15, it doesn't matter what units we have here. Let's go with square inches, just because 15 square meters is a pretty big pipe. Over here on the other end, this is going to choke down to 4 square inches. Okay, so those are my areas. Let's pretend here that I've got water that's flowing in this pipe at a velocity of 6 meters per second, and that water is going to come here. All this water has to come like this. You can see that that's already those lines are coming together. It's going to have to go a lot faster here. this is relatively slow. When it chokes down, it has to speed up in order to get all of that water out of the pipe through a smaller diameter, through a smaller area. So all we have to do is we write down V1A1 equals V2A2. If I know the velocity on this side, then I can use that to find the velocity on the other side. So right here, V2 would be equal to V1A1 over A2, and my velocity on side 1 was 6 meters per second. A1 was 15 square inches. I'm dividing that by 4 square inches. Not really sure why I can't pick numbers that are easy to work with today, but let's do 6 times 15 divided by 4. Would be 22.5. So that's a, where am I? Right here, this one. Okay, 22.5 meters per second is how fast the water has to flow on the second side over here. You see this in rivers, right? If the river's big and wide, then the river just kind of dawdles along, and you know, the sunlight sparkles and the water bugs flit across the surface, and it's a nice time to put your paddle down and eat a lunch or something. When it gets fast and pinches down close, you know, and the banks come in, then the water's going to speed up and everything gets a little more exciting, right? So same thing in a river. Here is the next equation that I'd like to show you. This is called Bernoulli's equation, and once again we're talking about fluid moving in a pipe, and that's all this chapter does really. So it could be a river, it could be a pipe, it could be anything, but I've got fluid that's contained in some kind of channel and it's flowing, and once again I want to pick a point down here, call that point 1. I want to pick a point somewhere else on the pipe and call that point 2. And anytime I have a setup like this, whether the pipe gets smaller, bigger, whether it goes up, down, whatever happens, Bernoulli's equation here, this big mess, is the equation that links several variables together. The variables would be pressure, right? P1 is the pressure at this side, and P2 would be the pressure over here. Right, P1, P2 would be the pressure and the pressure. The D for density, you could use rho there as well. GH1, how much height do I have at this level? And then H2 would talk about the height at some other level. It could go up or it could go down. You know, maybe the pipe drops or maybe it gains or something. Whichever way, I can put that in and see what happens. In practice, what's kind of nice to do is to pick the lower level, H1, and just call that 0. All we're really interested in is how high up did it rise, or how, you know, if it did fall. I can call anywhere I want to 0. I could call the middle 0 if I wanted to, and this is, you know, down 2 meters and up 3 meters or something. But if the thing rises 5 meters, I would call the bottom one 0, and then say the water goes up 5 meters. Okay, and then lastly here, the velocity of the fluid right there. V1 and V2 would be the velocity at point 1 and the velocity at point 2. We've already seen the equation of continuity. That last thing, that still applies, that still holds. So we're going to use Bernoulli's equation here in tandem with V1A1 equals V2A2. And you can see how this guy and this guy, those are going to be tied together. Whatever fluid I push into this end of the pipe has to come out at the same rate on this end of the pipe. That's assuming the pipe is full, right? If the pipe's only half full, then I've got some room there, and that isn't necessarily true. But we're talking about full flowing pipes here. I've got these two equations to use together. Let me just point out some things about this Bernoulli's equation, though. This is kind of interesting. Will you allow me to change a letter here real quick? Could I change this D to an M? And I'd have MGH1 plus 1/2 MV1 squared. Doesn't this look familiar? Over here, this would be MGH2 plus 1/2 MV2 squared. That's what we wrote down over and over in chapter 7 for conservation of energy. And so this really comes out of conservation of energy and is a part of conservation of energy. The part that wasn't in chapter 7 is this pressure, right? And pressure is a form of energy. It's the thing that pushes the fluid forward. So it needs to go in there as well. When we've got those three pieces, here's the pressure. You could think of this as the potential energy term right here. And the kinetic energy right here. Then the pressure plus the potential energy plus the kinetic energy. I have to conserve energy again. I have to have the same amount on both sides. There's no magic source of energy that appears out of nowhere. Neither does it disappear into nothingness. So it's got to be the same on both sides. Let's set up one of these and see what happens. Very often when you have a building, there's a big pipe at the street level, or actually below street level. They dig a hole, and put it down in there, and then the pipe will come up, and up at the top of the building you've got a smaller pipe. So down here's a big pipe feeding the whole building. By the time you get to each toilet and water fountain and sink and whatever, you're down to a half-inch pipe or something, right? So the big pipe goes down to little pipes, and that's what I'd like to draw here. I'm thinking about 0.1 down here at the street level, thinking about 0.2 up here on the 4th or 5th or 16th or 6,000th story, whatever you have. We'll make up some numbers for all of this, but let's see what the implications here are. If I have the pressure at this end, city pressure is something 35 to 50 psi, something like that. Let's put in 35 psi. We don't really want psi, so I'm going to convert that over to Pascal. Remember that 14.7 psi was the same thing as 1.013 times 10 to the 5th Pascal. And so we can use that to convert our units. I'm going to do that right now. If I can get rid of this, here we go. 35 times 1.013 E5 divided by 14.7. Those were the two values of atmospheric pressure, so it's a good easy way to remember those. 241,190, pick a number somewhere in there. Come back. There we go. My pressure at this side is 241,000 Pascal, something like that. Okay? And I'm going to make up a number here. Let's say the velocity on this end of the pipe is something relatively slow, 6 meters per second. The cross-sectional area down here, if I knew that, let's say that I've got a pipe that's, these are pretty big pipes, 8-inch pipe maybe, if it's a big building. If it's 8 inches in diameter, then let's do a couple things. Let's say that D1 equals 8 inches. We'll convert those over to centimeters, and then we can make meters out of that. So 1 inch is 2.54 centimeters. If you want, we can just go ahead and make that 0.0254 meters. Get this done all at once. And calculator's right here. 8 times 0.0254 would be 0.2. So let's go with a diameter of 0.2 there. Wrong. This one, okay, equals 0.2 meters. Okay, I need to calculate the cross-sectional area there. So remember, the area is pi r squared or pi diameter squared divided by 4. Either way you want to do that. If I take pi times the last answer squared and divide by 4, then I would have 0.03 24 square meters for my cross-sectional area. That's the number that I'd like to put down here at the bottom. 0.0324 square meters. The other number here that I have to have is the height. And remember, I said I usually like to call the bottom one 0. So we'll just put in a 0 right there. Okay. Now let's make up some numbers for the top, and we'll see where this takes us. All right. I'd like to know the pressure at the top. That's one of the questions. I'd like to know the velocity of the fluid at the top. If the pipe had a diameter of 1/2 inch, we'll come in right here and say D2 equals 0.5 inch. And that's kind of standard for plumbing, 1/2 inch PVC or PEX or whatever you're using. If I go 0.5 times 0.02, where was that number? Oh, 54, right. 0.0127 would be the diameter up there. 0.0127 meters. I could calculate my area up there. Again, pi diameter 2 squared divided by 4 and get that number. So that would be pi times the second answer squared divided by 4 is 1.3 times 10 to the negative 4. A little bitty cross-sectional area. And 1.3 times 10 to the negative 4 square meters on that. So we've got our area now. A2 equals 1.3 times 10 to the negative 4 meters squared. The other number that we need to know is the height. How high up does this go? So let's make H2. Currently I'm sitting 4 stories above the ground here at the Northeast campus, and if we allow, 4 meters for every floor, that would be something like 16 meters up in the air. All right. So what we'd like to do is to find the pressure up here on the 4th floor, and we'd also like to find V2. All right. So here we go. I have 2 unknowns. That means I have to have 2 equations. The first one that I want to use is the equation of continuity. A1 V1 equals A2 V2, and here again we can solve for V2. So that would be A1 V1 divided by A2. I have all those numbers, so this would be 0.0324 square meters, moving at 6 meters per second at the ground level. Up at the top, I've got a much smaller area pipe. Those are going to cancel out and just leave me with meters per second. Let's get that number real quick, if I can remember all those. 0.0324 times 6 divided by that last number that we just had. And 1,500, is that right? I should have picked a smaller number at the bottom. We'll put this down, but that's kind of a ridiculous number. 1,534 meters per second. Okay, we'll work with it. It'll be all right. What it's going to mean, though, is that I don't have enough pressure, or I don't have enough flow up there at the top, and I'm going to have to put a pump in, which is kind of the point of where we're going with this anyway. So when we do Bernoulli's equation, let me check that one more time. 0.0324 times 6 divided by that little bitty number. Yeah, it's going to be big, isn't it? Okay, so maybe I should have picked some different numbers. Let's see what happens here. We're going to end up with a negative pressure, though, almost certainly, which is bad. And let's see what happens. I know what's going to happen, but let's do it anyway. We write down Bernoulli's equation next. This was the equation of continuity. and that supplied one of these numbers for us. That one has fewer variables, so we want to do that first, and get our other velocity. Okay. The pressure then at the top, that's where I'd come in with Bernoulli's equation. And right here, it's a chore to write all that down, and I apologize for that. But if you try to remember it as pressure plus potential energy plus kinetic energy, then it's just going to be the same on both sides. You do need to watch your units pretty closely here and make sure that everything's going in standard units. If this is in Pascal, then this should all work out to Pascal, and that should all work out to Pascal. Okay, that will happen if you're working in kilograms and meters per second. If the density is in kilogram per cubic meter, or per, you know, and if you just stick to all the standard units, this will do fine. All right. We did say that H1 is equal to 0, and you can see the benefit there of having a 0 lying around. You get to cross off one of these terms. I'm looking for P2, so I'm going to leave that on the right hand side, subtract the other two terms, and I'll have P1 plus 1/2 rho V1 squared minus rho GH2 minus 1/2 rho V2 squared. That last term there on the left is the one that's going to blow this up and make it a big mess, and the math that I'm doing is still good. What I should have done is put the 35 psi up here. I need the right pressure on the top floor to fill the toilets and to make the water fountains run and to get water out of the sink. So I really need 35 psi up here, which means that I've got to have a bigger pressure down here to push it up there, which means I probably need a pump. Okay, somebody's got to do this problem every time a big building gets built, and say, how big of a pump do I need to put down there? I should have set the 35 up top. I didn't. That's my fault. And we'll just see what happens here. But this is about to blow up on us, so let's see how ridiculous it is. We have these numbers then, and we can put them in. The pressure at side 1 was 241,000 Pascal. I need to say plus 1/2 the density. I'm pushing water through this pipe, so the density of water again is 1,000 kilograms per cubic meter. And the velocity at side 1 is 6 meters per second. That gets squared. Then I'm subtracting. I'm on this third term right here, and what an awful color. And so let's do that one now. And so this would be minus the density is 1,000 kilograms per cubic meter. Put all your units in here and watch them, see what they do. 9.8 meters per second squared, and the height up there was 16 meters. And I'm going to have to skip down here and get that last term. Minus 1/2 the density, 1,000 kilograms per cubic meter. We're almost done, I promise. Here's that awful 1,534 meter per second. Remember, that's got to get squared too. Don't forget your squareds. Okay, so I fully expect this to blow up in my face, and we'll find it hard to believe if it doesn't. Let's see what happens. If I take 241,000, then I need to subtract the kinetic energy term at the bottom. That was 0.5 times 1,000. No, actually I'm adding that one, I'm sorry. Times 6 squared. And we'll glance back at the thing, make sure we're getting this right. Here's the 241,000 Pascal. My goodness, wrong end of the pen there. 241,000 Pascal. All right, laser, please. There's the pressure that we put in first, plus 1/2 1,000 times 6 squared. So we've got that. Next, we need to subtract the potential energy term, if you will, at the top. And so we'll put that in right now. And we say minus 1,000 times G times the 16 meters of height that we have there. And then we need to subtract the kinetic energy term at the top. Minus 5 times 1,000 times the last number that we calculated there, 1534 or 5 or something, squared. And when I hit go, I get a negative number. Negative pressure is bad. Okay, that's a vacuum. You just broke all your pipes and everything. Okay, effectively this is saying you don't get any water on the top floor. So now that we've got the number 118,000 Pascal, something on that order. Okay, we can see that this does not work. All right, and our plumbing system, we are not going to get the pressure that we need up on the top floor, so we have to do something else. That something else would involve either higher pressure from the city or installing a pump to pump water up to the top floor. I have heard of skyscrapers in New York City and stuff, and they hook up the fire sprinkler system, 40, 50, 80 stories up, and they just hook it up to the city pressure, right? It's 35 psi. That's just not enough pressure to push the water 800 feet up in the air. You've got to have a pump there to run that. So the other thing you can do, and in big cities like New York, they very often you'll see a big tank up on the roof itself, and then you could pump water up to that tank and have a reserve there. Even if the power went out, then you'd have gravity pulling that water, providing pressure down below. So if you had a fire, you could still have water. A water tower works on the same principle, right? Let's do this problem one more time. Let's do it the right way this time. I apologize for that. And these are so much fun. I know you want to do another one. So let me do the pipe, and here it gets small. We've already got all these numbers, so hopefully we can do this pretty quickly. This time let's set it up right. I need a certain pressure at the top. That should be the 35 psi or whatever it is. We had that number on the last screen, which was 241,000 Pascal. Okay, the height, and this should be P2, I'm sorry. H2 is still 16 meters. The area of the pipe, we still have that, although I've completely forgotten it. 1 point, where'd it go? 3 times 10 to the negative 4. And that would be in square meters. Don't know the velocity just yet here. So we'll have to get that. But let's say that I need the water to flow at a certain rate. Okay, why don't we make up a number here? People on the top floor expect there to be enough water and enough pressure to deliver that water there. I don't know what that number is. I'm going to make up 4 meters per second, something like that. What am I missing? That's probably good. All right, let's set our expectations on what we need to have at the top, and then figure out what we have to have at the bottom. Pressure 1 at the bottom, we're going to leave that one a question mark. V2, that'll be the other question that we have here. The height is 0, and the cross-sectional area, these should be 1s, we said was 0.2 meters, I want to say. Indeed, it's right there. Okay, so 0.2 meters is the number that we need. Come on, please. My computer's mad at me. Stalling out. Come on. And apparently it got excited. Oh, yeah, I guess I did do that, didn't I? A couple more slides there. All right, I already forgot. 0.2 meters. Here we go, squared. Okay? So I think that's everything that we need. Again, do the equation of continuity. And right here, I have the cross-sectional area times the velocity. It's got to be constant. So it would look like that. We're looking for the velocity at end number 1. So we do this, A2, 1.3 times 10 to the negative 4 meters squared. V2 was 4 meters per second. Area 1 is 0.2 meters, and we'll get you a number for that right away. 1.3 e negative 4 times 4 meters per second, and then we're dividing by the 0.2. 0.0026 is a number for that. Meters per second. Okay, I've got a big pipe. I don't need a whole lot of flow rate here. Pretty slow flow rate here means when I get up to the top floor and it pinches down, then I'm going to have my the 4 meters per second that I need, or whatever the number is. All right. Here is Bernoulli's equation then. And the most painful, there are two hard things about Bernoulli's equation. One is writing all this stuff down, of course, which is pretty grievous, I agree. The other, the most difficult thing about Bernoulli's equation is trying to remember how to spell Bernoulli. But here is Bernoulli's equation. Again, H1 is equal to 0, and it looks like that. I'm interested in pressure 1. How much pressure do I need to push to get all that water up to the top floor? And so we will solve this thing for P1. That's going to be equal to P2 plus rho GH2 plus 1/2 rho V2 squared, and I'm subtracting this term from both sides. So I'll put that right here. Pressure 2 was the 241,000 Pascal. Here's plus 1,000 kilograms per cubic meter, density of water, times G, 9.8 meter per second squared. The height at the top was 16 meters. That takes care of this. So I've done the first term, done the second term. Moving on to the third, 1/2 times 1,000 kilograms per cubic meter. The velocity at the top needs to be 4 meters per second. That has to be squared, so that's the third term checked off. And then lastly, I subtract the kinetic energy at the bottom, and it was moving a scant 0.0026 meters per second. I know you can't read that, and I apologize, but that's that. I'm going to just do this on my little handheld calculator here. You've already seen it. 241,000 plus 1,000 times 9.8 times 16 plus 0.5 times 1,000 times 4 squared minus 0.5 times 1,000 times, what is that number? I can't read it now. 0.0026. And I left off the squared on that, so don't forget to square that number right there. Okay. Down here at the bottom, I need a whole lot of pressure. I need to have 406,000 Pascal. Okay. That's about twice, what I would need at the top. But that extra pressure is going to deliver that water up there for me. That means that I need to go buy myself a pump, and you could look at the tables and see what size pump you need to get all that up there. And but that's the kind of thing that you can do with Bernoulli's equation. This would work with fire hoses and a garden hose and in any kind of moving fluid. Bernoulli's equation tells you everything that you want to know about it. Now I've got some extra formulas here that I wanted you to see. This is called Torricelli's theorem, and the thing that's kind of nice about this is it says if I've got water that's coming out some height below the water level, let's say I've got a big tank and I shoot a hole in the bottom of it, right? This formula right here would tell us how fast that water is going to come out of the tank. Okay, this actually comes from Bernoulli's equation. Let me show you what I mean by that. If I come in here and write down Bernoulli's equation, I want to copy paste this where I can just drop it in when I need it, Here is Bernoulli's equation, and as always, we're going to pick 2 points and do that. So the 2 points that I would like to pick this time would be this point right here. I'm going to call that point 1, and this point right here, point 2. And then we have to kind of make some assumptions here about what's going on at those 2 points. But we want to look at what's happening right there. Those are on the same level, right? So H1 is equal to H2. And if they're the same thing, when I subtract it from one side, it's going to get subtracted from the other side. So that automatically crosses off those, quote, potential energy, unquote, terms right there. If I subtract it from the left, it's going to be the same number that it would be on the right. They both cancel. Okay. Now here's where you could argue, I guess. I certainly have some velocity. This point right here, that dot of water is moving away at V2. Maybe this is a simplification, but the dot inside the tank is not really moving. A molecule of water right there is effectively just waiting for its turn to get to the hole, and then it goes zing out the hole. But before it gets to the hole, we say its velocity is 0. Okay? So if V1 equals 0, then this crosses off, and I don't have to worry about that term. Here's the next step. This fluid right here, H1, is down below, so I know that when fluid is below the surface, that I can use the pressure at a depth formula to find out how much pressure I have. So the pressure at point 1 is going to be the density of the fluid times G times H1, and we can put that in right here. Rho G H1. These 2 terms are gone, and so I get to the equal sign right there. The pressure, the molecule of water over here that's already shot out of the tube isn't under any water. The height of water that it's under is 0. So right here, I would say P2 equals 0. Again, there's no water pushing down on it from above. So all I have left on the right-hand side would be 1/2 rho V2 squared. I've got a rho on each side. Those are going to cancel out. I multiply both sides by 2. That gives me V2 squared. And then I take the square root of both sides. 2gh equals the velocity. That's Torricelli's theorem. It's called a theorem because you can prove it, and we just did that. All right, but it's kind of a handy way to know. If I have a hole that is some depth below the water surface, then I can tell you how fast water is going to be coming out of that hole. All right, won't do one of those, but I think you can see where that turns out. Here's another freebie here. This is called viscosity and Poiseuille's law. This is an interesting formula if we want to think about the flow rate, how much water is flowing through this pipe. R for flow rate. We also said that was velocity times area, right? So that would be another way to go here. But that flow rate R is going to be equal to pi r to the 4th times delta P over 8 eta L. Now, again, this is a freebie. We're not going to go into much depth here, but L is the length of the pipe, and you can see that as this number gets bigger and bigger, I'm going to have less and less flow. There's frictional forces. There's drag on the water in the pipe, and so you're going to get less and less water. You know, it's easier to push water through a short pipe than a really long pipe. Okay, so that's got to go in there. This delta P says I've got a certain pressure on this end of the pipe and a certain pressure here. If those numbers are the same, if I had if I had 100 psi here and 100 psi here, those forces cancel out and the water doesn't flow. So I need a change in pressure. If this is 80 psi here, now I've got a pressure drop, a pressure difference, and it's pushing harder on the left-hand side than on the right. So that's going to determine how much water, how fast the water flows through the pipe. I need that in there. The greater the delta P is, then the greater the flow rate is. The radius right here would be the radius of the pipe. And so the bigger that is, then the more water I can push through it. This eta, though, this is the new guy right here. That's called viscosity. And that's basically a stickiness, or almost like a fluid friction. How easy is it to push this fluid? Here's two examples. If I take water, I can push that through a pipe pretty easily. If I take pancake syrup, you know how thick and sticky that is, right? And then it doesn't flow really well. And of course that viscosity changes. If you have cold pancake syrup, if you get mixed up and put your syrup in the refrigerator, good luck getting it out, right? It's really thick and sticky. That stickiness, that friction, that resistance to motion is this viscosity. Eta is the name of that Greek letter right there. And you put that number in. There are ways to measure that or look it up, whatever you need to do. You probably know that if you put the syrup bottle in the microwave, then you warm that syrup up and the viscosity goes down. It gets easier to flow through that. So here again, if I have a big viscosity, when I divide by that big number, that's going to give me a small answer, and I'm not going to get a whole lot of flow through the pipe. Okay, so that's kind of an interesting formula. It's not in the book, but I wanted you to see it and kind of be aware of it and know that if you ever need it, you can go look that up and see what happens. I've got one more of the same category here. This is called the Reynolds number. The Reynolds number is a number that you can calculate with moving fluids. The things that you need to know here would be the density of the fluid, D, or again you could use rho, either one. V would be the velocity of the fluid, so I need to know how fast the fluid is moving. D would be the diameter of the pipe, and then there's that viscosity again. So what we're thinking about is fluid flowing through a pipe. This Reynolds number tells me, does the fluid flow nice and smooth and straight? Is it these layers of fluid that flow easily through the pipe, or is it turbulent? Is it all mixed up and roiling about to make a big mess? And that's going to provide more friction. So when you calculate this number, three things can happen. If N sub r, if the Reynolds number is less than a certain amount, then you get laminar flow. If this number comes up small, then all the fluid's flowing through very nicely. All right. If you get a big number there, over 4,000, then the fluid's doing this kind of thing. You can see why that would be. If you try to push the water too fast through the pipe, it's going to get all mixed up. Or if the viscosity is very high, right? Or if the diameter, if I had a bigger pipe, then I can push more water through it without it getting turbulent and stuff. Anywhere between 2,100 and 4,000 is kind of transitional. It's it's not quite straight lines, but it's not all mixed up either. So it's kind of going from one to another. So that's the last of the things there. Probably not on the test. Definitely not in the book. I just wanted you to see it. And if we're going to talk about fluid dynamics, that is a part of it. And some good stuff there. Very good. Thank you for everything. Hope you've enjoyed it, and have a good day.